Today we are beginning our unit on linear functions, and we're going to start by just defining what a linear function is and take a look at graphing using a table of values. Remember, you are watching, you are listening, and you are taking notes in your booklet on page 1. So let's start by putting our name and our class periods so that if it gets left behind, we know who to return it to. Then we're going to go through some definitions, starting with linear function. A linear function is a function whose graph forms a line that is not vertical. A vertical line is still linear, but it's not a function. We will talk more about that later. A linear equation is any equation that can be written in standard form. Now that definition doesn't really tell us very much, so we need to talk about what standard form is. I'm going to give you the formal definition first, and then I'm going to give you a description. The description is really more helpful than the formal definition. So our formal definition of standard form: ax plus by equals c, where a, b, and c are integers, and a and b are not both zeros. Let's talk about a couple of pieces of those. First, integers. Remember, those are our numbers, 0, 1, 2, 3, 4, and then the negatives, -1, -2, -3, -4. And then a and b cannot both be 0. A can be 0 or b can be 0, but they can't both be 0. These definitions are our formal definitions. Let's take a look at our descriptions, because that's the one that's really going to help. So when you have an equation that is written in standard form, all of the following are true. X and y both have exponents of 1. That is key. That is really what makes it linear, is the exponents of 1. X and y are not multiplied together. They do not appear in denominators, exponents, or radicands. Notice the word not there. So in other words, I don't have 1 over x or 1 over y. I don't have 3 to the x. That would be in the exponent position. And radicands is our roots, so I don't have the square root of x. So these are all no's. Again, for a function to be linear, your x and y will both have an exponent of 1. They will not be multiplied together, and they will not appear in denominators, exponents, or radicands. So x times y, that's also a no. We will talk more about this and do some sorting to figure out which functions are linear and which functions are not linear. But for now, we're going to move on to graphing using a table of values. All right, we have this function here. We're asked to graph it. 2x minus y equals -3. First, let's talk about why this is linear. The x and y are both raised to the power of 1. They are not multiplied together. There are no fractions, there are no roots, and there are no variables in the exponent position. If I'm looking at my definition, my a would be 2. That's my a. My b would be -1, and my c would be -3. So that's falling into place for my standard form. If we want to graph using a table of values, we're going to follow a couple of simple steps, starting with solving for y. That just makes our table of values easier to create. Then once we have our table of values, we'll plot our points, connect, and extend through. Let's start by solving for y. So I have 2x minus y equals -3. When I'm asked to solve for y, I am looking to isolate the y using my inverse operations. So I'm going to start over here with my 2x, and I'm going to subtract 2x from both sides. 2x minus 2x is 0, leaving me with negative y equals, I'm going to put my x first, negative 2x minus 3. I don't want negative y, I want y. So I'm now going to divide by negative 1, which is just going to change all my signs. So that's going to be a positive 2x plus 3, dividing by negative 1. My next step is to create my table of values. This is going to require a little bit of work that I'm going to kind of do down at the bottom. You can do wherever it works for you. And I'm going to randomly choose values for x. I say random, but really they're not random. I'm going to choose values that are easy to plug in, and that will give me my graph. I can really use whatever values I want, but I'm going to use small values so that they'll fit on this grid here. So the values I'm going to use for my table of values are going to be negative 2, negative 1, 0, 1, and 2. I really only need to do 2 points. I'm doing 5 just to give us a good view of what we're doing. And what I'm going to do is take out the x and plug in negative 2. Take out the x and plug in negative 1. Take out the x and plug in 0, and so on. So I'm going to start with my x equals negative 2. So my y will be 2 times negative 2 plus 3. Doing my arithmetic, negative 4 plus 3, which is negative 1. So my first point is negative 2 comma negative 1. Now I'm going to plug in negative 1. So when x is negative 1, y is 2 times negative 1 plus 3. Completing my order of operations, negative 2 plus 3, which is 1. Continuing along, when x is 0, y is 2 times 0 plus 3, which is just 3. And when x is 1, y is 2 times 1 plus 3, which is 5. I've run out of room, so I'm going to do 2 in my head. 2 times 2 is 4, plus 3 is 7. You'll notice there's also a little pattern happening here. Negative 1 to 1, 1 to 3, 3 to 5, 5 to 7. I'm adding 2 each time. Okay, plotting my points. Negative 2 comma negative 1. It's going to be right. Let me see if I can do that better. There. Negative 1, that's not right. Let me try again. Negative 2 comma negative 1 is right there. Then negative 1 comma 1. Zero comma 3. 1 comma 5. 2 comma 7. Notice the straight line that forms. That's what makes it linear. So our equation follows the properties or the description of our linear functions. X and y are both to the first power. They are not multiplied together. They are not in a denominator, in a square root, or in an exponent position. So if all those things are true, it's going to form a nice pretty line. Remember, I chose these values, but I could have chosen larger values. I could have chosen my fractions and decimals. So every single point that is on this line actually makes that equation true, which is why I connect and extend through. So every point on that line makes this equation, which is equal to this equation, true. And that is how we graph our linear functions using a table of values. We will be practicing this a lot more because it's an incredibly important skill for us.